Hi guys. Okay, we're gonna continue our conversation about atoms, but I mentioned some things in the previous atom videos that we could go into more detail about some of the features of the Bohr model of the atom. And in particular, what we want to study in this video is subshells. So what we mean by that is that these electrons can go, don't forget, they can go to the n equals 1 level, and that is the lowest level, and then there's the n equals 2 level, and there's the n equals 3 level, and they will try to fill up this lowest level first, and then they'll continue to fill up the second level, and as many electrons as you have, they will continue to pack in as low as possible in a low energy configuration. And kind of the same way that, like, if you put a bunch of balls in a hill, they're all going to fill the bottom of the hill before they fill the top of the hill. And so if you excite them now, you can actually kick one up and then it can fall back down again. So that's actually a lot like these are. So we're going to modify this so that we see that each one of these is a little bit like the floor of a building. So you might have like the first floor of a building. So I'm going to go ahead and draw a building here so that we can get a sense of that. And we have here the lowest part of the building is level 1, level 2, level 3, level 4, level 5, level 6, level 7. Now the thing is, we were talking about shelves before, so what we can say is that each of these levels, n equals 1, n equals 2, n equals 3, n equals 4, has an entire floor dedicated to it, but then within that floor, each one has the ability to have shelves on it. So you can have, let's put this in like a different color, so we'll put like just a red shelf here, okay? So it has one shelf where you can put things on floor 1. On floor 2 there are 2 shelves. On floor 3 there are 3 shelves. So I gave you some numbers with how many electrons are allowed to be in here on each of these floors, and this is actually the reasoning why. So we're going to refer to these as, so we have n is the principal quantum number, okay? And then we have subshells, which are given as L. So you can say that these are now going to be L is equal to, and then we usually refer to these as S, P, D, and F. And then you can actually keep going. So S, P, D, F, G, H, I. And so they just keep going, right? But it starts off at S, and the reason for that is kind of historical, and we'll go into that in just a moment when we talk about Bohr and how genius he was, and why people named these this. But for right now, let's just say S stands for the first shelf, and then P stands for the second shelf, and D stands for the third shelf, and so forth. Okay, let's take a look at our atom. So this is the same concept as what we had before, right? Except for this time we have the n equals 1 here, so we'll put that in. So this is n equals 1, this is n equals 2, this is n equals 3. But now, instead of just being one ring, each one of these actually has what we call a subshell in there. So the subshells I will label in red. Subshells. Not to be confused with this nucleus in here. Now, we have studied the nucleus, and we've studied kind of how many protons, how many neutrons, and so forth. But now we're going to be looking a little bit more detail to what the electrons are doing and why chemistry even occurs. So let's go ahead and put our electrons in our different shelves. Okay, so what did we say S is? You could say S stands for shelf, like the first shelf, right? So this one, n equals 1, our first and lowest floor of our building, our first and lowest level of our atom, has one subshell, and it is S. Everybody has an S. That's not special. Okay, so this is this is S. Okay. Now for our second one, this goes to n equals 2. So when we go up to the next floor of our building, we now have options about which shelf we want to be on, the first shelf or the second shelf. Once we go up to the third floor, we now have even more options about where we want to be, the first shelf, the second shelf, or the third shelf. And it's just going to continue doing that for as many levels as you please, right? So as we said, we're going to fill up our electrons on each of these levels. So each of these starts to have, this is kind of interesting the way this plays out, okay? So we start off with our subshell, let's write it like this. Our subshell S has got a double seat in it, okay? So it can allow 2 electrons. And then P, well, that one has a double seat, and then it also has another double seat on each side. So it actually has a total of 6 possible places to put electrons. And then D, well, that has a double seat, the same double seats that P had, but it has an additional 2 on each side. So it's just going to keep doing this, right? So, and then F, same thing. We're going to have double seat, same double seats that D had, but we're going to include another one. So we're kind of making a pyramid out of this, right? Okay, so let's count these up. Let's count these up and see if we can arrive at the same conclusion that I gave you in the last video, except for I just sort of threw numbers at you and gave you like, oh, an electron could be here, an electron could be there, without any reasoning on it. But now we can actually anticipate why. The first, n equals 1, has only the S shell. So we take 1 electron and we put it in one of these, and we put another electron and we put it in one of these. Okay. The P shell has 1, 2, 3, 4, 5, 6 different places. So once we go up to n equals 2, we can't do anything else with n equals 1. There is no more shelves. There's no more places for electrons. We go up to n equals 2, and we now have an S and a P that we can deal with. And so the first one we'll actually put 2 electrons on, and then the P we can actually put 6 electrons on, so we'll do that. Like that, right? D now, so we're done with the level 2. There's no more options, we can't put any more there. So level D subshell D is only going to be involved once we get up to level 3. So we get n equals 3, we continue stacking electrons, and let's go ahead and stack, let's say 5 more electrons, okay? So what we're going to do is we go up to n equals 3, and we have how many electrons in the first one? We have 2. How many electrons in the second one? We have 1, 2 for the S shell, and then 3, 4, 5, 6, 7, 8 for the P shell. So that means we have 8 and n equals 2. And then we're going to keep on until we get 5 more electrons, because we might say, let's see, this is 2 and this is 8, and if we had 5 more, that means we had a total of 15 electrons. I'm just throwing a number out there we can try, and let's see what element it is when we're done. So we're going to keep on packing this in, okay? So let's start back over again. We have the n equals 3 shell now, and we have 5 electrons in our n equals 3 shell. Let's figure out what we're going to do with them. We're going to go, we could have had 6 or 7 or whatever, but I chose 5 in this case, okay? Because we're not going to fill it up entirely. We filled this one up, we filled this one up, and then because we only had 15 electrons, so we put 2 of them in the bottom. The next 8 of them went into the second layer, and then we ran out of space, so the remaining 5 of them are going to go into the third layer. So let's do that. Okay, well, first of all, we get 1, 2, so we get 2 of them in our S shell, and then we're going to say, okay, that's 2 out of 5, so we have 3 left, and we'll go 1, 2, 3, where the P shell here, this P shell here, is going to have 1, 3, and that's what our atom would look like. Okay, so this says that we have 15 electrons total, and let's take a look at what that atom is. So we'll look at our periodic table here, and we're going to go through the same process where we put together our electrons. Okay, so I said we had an element that had 15 electrons, and what we're going to say is it's a neutral atom in its ground state. So we have the number of electrons is equal to 15 electrons. Let's count through it. We have hydrogen would have 1 electron in the n equals 1, and then the s shell. Helium would have n equals 1, would have 2 electrons in the s shell. Then lithium is the next one in line, and that one would have 2 of its 3 electrons in the first layer, and then the third one would be stuck up here in the next available layer. S, the n equals 2, but the s subshell. Beryllium has another electron here, right? And so we filled up the n equals 1 s subshell, and we filled up the n equals 2 s subshell. And now when we go to boron, we can now fill up, we can start to fill up the p subshell. Notice here what we have is 1, 2, 3, 4, 5, 6 of these, right? That's not a coincidence. This is actually, this block here represents those 2 that we put in the s subshell, and then this block here represents the ones that we put in the p subshell. So we begin filling up our, when we get to boron, we need to have the next one go to the p shell, because there's not enough room in the, so we have n equals 1, we have n equals 2. There's not enough room in the n equals 2 shell in the s subshell because we filled it. So we have to begin filling the p subshell. So here's that electron that gets shoved into the p shell, and that's for boron. If we did carbon, then we'd have 2 more, so we'd have to, instead of 1 more, so we'd have to put 2 of them in the p shell. For nitrogen, well, we need to put a 3rd one. Oxygen, fluorine, and neon. So this final one. Now what happens is that we have completely filled our n equals 2 level, and this is actually, this is a happy atom, because if you can have a neutral atom that has its shells filled up, well, that sure is, that's a very happy atom. Usually atoms don't get to be that happy. Usually atoms are either, they're not neutral, they're positive or negative, or they have their shells filled, but they don't usually get to have the best of both worlds. So in the case of neon, which is where we landed, we have 10 electrons here, and this happens to be, it has 10 protons, has 10 electrons, and all of those electrons very neatly fill that shell. If you had take one away and you have 9 protons and 9 electrons, then that shell would not be entirely filled. It would be missing an electron. That's a very unhappy atom. Fluorine is not a very happy atom. So we can continue now, because we said that the number of electrons in our particular atom on the previous page was not 10, it was 15. So let's keep going until we get to the atom that belongs here. Let's see, if we added another one, it would be sodium. So now what we're doing is we're moving up to the n equals 3 shell, and in the n equals 3 shell we get sodium has another electron, and then magnesium has another electron. So now we've just filled up the n equals 3 s subshell, and then we skip on over to here to aluminum. Okay, still on that 3. So we skip on over to aluminum, and at aluminum we say, well, let's We need to add another electron. We're out of S subshell, so we begin to go to the P subshell. Here, so we have one for aluminum, and then if we go to silicon, well, then we have another one on the P subshell, and then we go to phosphorus, we get another one in the P subshell, and then we go to sulfur, we have another one in the P subshell, and we go to chlorine, there's another one, and then one more, argon. Now we have not filled up the entire n equals 3 level, but we have filled up the P shell, and generally that's what makes the atoms happy, is filling up the P shell. Alright, now I think we passed our point that we wanted to get to, right? Because we said this has the electrons number of 15, and we went all the way up to 18, up to argon. So it looks like we need to subtract 3 of those. So there goes 1, there goes 2, there goes 3. We've actually gotten to phosphorus. Now you could have guessed that immediately if I told you this thing had 15 electrons and it was a neutral atom. Then that means that it has 15 electrons and 15 protons, which immediately makes it a phosphorus atom. I also stated that this was in the ground state, which means that we've packed in these electrons as low as they will go. None of them have tried to go up to the n equals 4 level or up to the D shell or anything like that. So okay, so this is generally how we talk about filling these up. All right. Now there's another way to write that, and it's going to be quite important in chemistry because the way we write this is we have a notation for this where we say if you have a 1 and then you have an S, then what that does is it says I'm at the n equals 1, and then this is my subshell. So this is your principal quantum number, and then this is the subshell. And what you do is exactly the same thing in writing that we did on our atom here. So we're going to write it out like this. For phosphorus, we would say, okay, let's count it out. We have 15 electrons, so we go 1, n equals 1, and then first we do the S shell. And how many can we fit in there? 2. So we're going to put a little, that's not squared, that's actually just a notation up at the top here, like a little hat, like an accessory that says, hey, I have 2 electrons in this particular shell. Well, we don't have any more 1s because there's only one subshell in the first n equals 1 layer. So we have to move on to 2. So we go to 2. The next one is 2. Now we do fill up another S subshell, so we're going to, that's this one right here, right? We're going to fill that up with 2 more electrons. And then what do we have? Well, we're still in the n equals 2 layer, so let's go ahead and write another 2. But this time, instead of the S subshell, we were going to write a P subshell, because this is the same process we did when we were just building atoms on our, electrons on our atom. It's just that we're writing it down differently in a different notation. Okay. So now we have, how many can we fit in that P shell? We can fit 6. So we'll go ahead and put a 6 here. Well, we ran out of room, so we have to go to the n equals 3 layer here, and we had an S subshell that we started with. We put 2 electrons in that, and then we moved on to the next part of the n equals 3 shell, and that has a P, and then we managed to only fit 3 electrons in there. Actually, I kind of shoved 6 in there before we sort of retracted that and made it the 15 that we started with. So let's go ahead and put this for the 15 that we started with, because this is phosphorus. We are only able to fit 3 electrons in. Now that could go all the way up to 6 if we wanted, but we don't have that. We've only got 15 electrons. So now if we are to add all this up, we can say, okay, this is 2, 4, and then plus 6 is 10, and then plus 2 is 12, and then plus 3 is 15, right? So that gives you an idea about how this is written typically. Okay. Now for shorthand, this could actually be rewritten because this whole section right here is the same as a neon atom. How do I know that? Well, if I go, this is 1s1, 1s2, right? And then I have 1s2, 2s1, and then 1s2, 2s2, so 1s2, 2s2, and then when I get to boron, now I have 1s2, 2s2, and then 2p1 because I've gone 1 into the p shell here, and then 2p2, 2p3, 2p4, 2p5, 2p6. So this notation for our neon atom would be 1s2, 2s2, 2p6. So another way to write this is just, hey, all that stuff is the same as neon, and then after I go through the process of building a neon, then I continue to build up my phosphorus atom. So that's just another way to do this on paper, so that you don't have to do it in by actually drawing each of the atoms on the, or excuse me, each of the electrons on this atom here. And it actually is pretty simple to do if you don't have a model of an atom here. All you have to do is just look at a periodic table, and you can easily see what order all these come in. So we could see then, well, once you get to the D shell, it does get a little weird, I have to say. All right, so this is the general idea behind subshells, which is really important for understanding chemistry, because the chemistry of things is primarily based on the S shell, P shell, and D shell interaction between things. So we have one more term that we need to pay attention to, and that is valence electrons. It's not a big deal. Well, I shouldn't say it's not a big deal. They are a big deal, but they're not hard to figure out. We went through this process of counting out. Essentially, it's like getting on a bus, right, and saying, hey, is there room on this row? No. Move to the next row. You move to the next row and say, hey, is there room on this row? No. Move to the next row. And you just keep doing that until you find a seat, right? And then you're going to keep building up these electrons, and then this last term here, or at least the term that is not entirely filled with electrons, that has a very important number in it. That is the valence electrons. Okay, so a lot of the interactions between atoms are determined by the fact that this outer layer here, there's an electron, there's an electron, and there's an electron, and you can actually have different atoms come together and be happier based on how they interact with one another, to share electrons, to borrow electrons, to reach a place of sort of atomic happiness. And that is, in essence, the entire concept behind chemistry. Okay, so those valence electrons are very important. Valence it's spelled like this. It's a term in your book. Valence electrons, valency. Okay, valency. Now, in other words, the valency of this is 3. So I'd say valency of 3 because it has 3 valence electrons. So that's actually the same term. Okay, it's just saying the same thing in different ways. Okay. Okay. So now notice one thing. There's only one group here that has a tendency not to have valence electrons after the p shell, and that is this last group right here. That is the one that I talked to you about before. Neon is very happy, argon is very happy, krypton is very happy. These are all very happy the way they are. We call them the noble gases or the inert gases because they have a tendency not to interact with other things, because if they have zero valence electrons, then they have zero desire to interact with other things. Okay. Hopefully this will give you kind of an idea behind why some of the things occur that we see in chemistry. But again, I really don't want to go too far into this. You should know what a valence electron is, and you know, basically how these things are structured. Okay. Okay, let's do our summary. Essentially, I want you to be aware, first of all, that the number of subshells in a particular atomic level is equal to the atomic level. So, in other words, if you have n equals 3, then it has 3 subshells, right? Okay. Now, the second thing that's important is that increasing subshell, and that is from S as the lowest subshell on up through the PDEF, is increasing that subshell results in an increasing number of seats for the electrons. So you remember you had one pair of electrons in S, and then you had 3 pairs in D, and then you had 5 pairs, in P, 5 pairs in D, and then 7 pairs in F, and it just keeps going from there. Okay. All right. The next thing is the electron configuration. And what we mean by that, what we're saying is, like, if we knew that we had an oxygen atom, we'd look at the periodic table and find out that a neutral oxygen atom has 8 electrons. So we would say, well, that's going to be the first set of seats is occupied by 2 electrons of the 8, and then the second one is going to be occupied by 2 more electrons out of the 8. So we have 4 out of the 8 total so far. And then we move on to the next one, which is 2p, and we have 4 electrons left. Well, we could have put 6 here total, but we only have 4 to give, and then that is then our oxygen atom. So that is the electron configuration and our process for building that. And then we also saw that that is visually, we're putting 2 here and 2 here, and then we're managing to put 4 on the n equals 2 p subshell, right? And that is oxygen atom. Okay. 4, we looked at the concept of valency or valence electrons, and that is what causes chemistry, essentially, right? Valence electrons are what causes atoms to interact with each other for the most part. There's a little bit more complexity to that, but for the most part, that is generally the way that chemistry occurs. Is by each of the atoms looks at each other and counts. Hey, how many electrons you got riding out on the outside of? How many electrons you have out in the doghouse, essentially, and that determines the chemistry. Okay. So hopefully this isn't too bad. I would like to connect this and the genius of Bohr in the next video to something called spectroscopy, so that you can have a sense of how the energy levels play out and introduce you to something called an electron